Have you ever stopped to think that almost everything you've learned about the universe since you were a child could be completely wrong? That the mental images you have constructed about the cosmos, about stars, about galaxies, about space and time itself, are actually comfortable illusions that we create to make sense of a universe that defies all our human intuition? Neil deGrasse Tyson, one of today's most influential astrophysicists, has dedicated his career to dismantling these comfortable illusions. And when you truly understand what he is revealing, your mind literally expands along with the universe he describes. Because the truth about the cosmos is infinitely stranger, more beautiful, and more disturbing than any science fiction has ever created. Imagine waking up tomorrow and discovering that gravity doesn't pull things down, that the vacuum of space isn't empty, that the Big Bang wasn't an explosion, that you're moving at millions of miles per hour right now without feeling anything at all, and that 95% of everything in the universe is made of something we've never seen, never touched, and may never directly detect. Tyson isn't just correcting little misunderstandings. He's demolishing the foundations of how we think about physical reality. And if you're one of those who love having your certainties challenged by real science, subscribe to the channel, because what we're going to explore in the next few dozen minutes will completely transform the way you look at the night sky and the very fabric of existence. The first big revelation that Tyson constantly emphasizes, and that almost no one really internalizes, is that the universe is not expanding into some pre-existing space, like a burst of fireworks expanding through the night air. When we think about the Big Bang, our mind automatically creates the image of a fireball exploding from a central point, hurling matter and energy in all directions across a vast spatial void that already existed before the explosion occurred. But this mental image, intuitive as it may be, is fundamentally wrong in a way that defies our ability to visualize. Space itself is expanding. It's not that the galaxies are moving away from each other through space, it's that the fabric of space between them is literally stretching, growing, creating more space where there was less space before. Tyson uses a fascinating analogy to illustrate this. Imagine a balloon being inflated with dots drawn on its surface. The dots are not moving through the rubber of the balloon. It is the rubber itself that is expanding, carrying the dots with it. But even this analogy has limitations because in the balloon there is a three-dimensional space around it where the air is, whereas in the real universe there is no outside for space to expand to. Space is all there is, and this expansion is happening everywhere simultaneously, among the distant galaxies, but also right here between you and the screen you are viewing now. Except that on the small scales, the fundamental forces like electromagnetism and gravity are strong enough to hold atoms, planets, and even entire galaxies together against this expansion. Inexorable cosmic. To truly understand why this revelation matters, we need to go back to the early 20th century, when humanity still believed the universe was static and eternal. Albert Einstein, when he developed his equations of general relativity in 1915, was disturbed to discover that his own equations predicted a dynamic universe, which was either expanding or contracting, but could not remain static. This bothered Einstein so much that he artificially added a cosmological constant to his equations, a phantom repulsive force that would counterbalance gravity and keep the universe perfectly still. But in 1929, Edwin Hubble made astronomical observations that changed everything. He discovered that distant galaxies were moving away from us, and not only that, the further away the galaxy, the faster it seemed to be moving away. The only explanation that made sense with Einstein's equations was that the universe was expanding. And if you imagine this expansion running in reverse, like a movie in reverse, everything in the universe would converge to a single point approximately 13.8 billion years ago, the moment we call the Big Bang. Einstein later called his cosmological constant his biggest mistake. But ironically, decades later, scientists would discover that something very similar to that cosmological constant actually exists, something we call dark energy, but serving exactly the opposite purpose of what Einstein imagined. Not keeping the universe static, but accelerating its expansion in a way that increasingly faster. Tyson often points out that when we look at the night sky, we are literally looking into the past, because starlight takes time to travel to our eyes. Light travels at approximately 300,000 kilometers per second, which seems absurdly fast compared to any speed we experience in everyday life. But on cosmic scales, it is almost painfully slow. When you look at the closest star beyond the Sun, Proxima Centauri, you are seeing light that came out of there 4.2 years ago. You are not seeing the star as it is now. You are seeing it as it was more than 4 years ago. When we look at the Andromeda Galaxy, we are seeing light that has traveled for 2.5 million years. We are literally looking at what that galaxy looked like when the first primitive human ancestors began to walk through Africa. The most powerful telescopes can detect galaxies whose light has traveled for more than 13 billion years. We are seeing the universe when it was just a few 100 million years old, still in its cosmic infancy. This means that there is really no now perspective on the universe. Each vantage point has its own temporal slice of the cosmos, and the further we look in space, the deeper we look in time. Tyson loves to emphasize this fundamental disconnect between our intuitive experience of a simultaneous universal present and the relativistic reality that simultaneity is an illusion. There is no cosmic now shared by the entire universe. Another profound revelation that Tyson constantly brings to light is the nature of the vacuum of space. When we think of outer space, we imagine a perfect void, a total absence of matter, an absolute nothingness between the stars and planets. But quantum physics reveals that the vacuum is actually buzzing with activity, a turbulent ocean of virtual particles that constantly pop in and out of existence on incredibly short timescales. These quantum fluctuations are not mere mathematical curiosities. They have measurable and observable effects, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a force of attraction because the space between the plates suppresses some wavelengths of the quantum fluctuations, while the space outside the plates allows the entire spectrum, creating a measurable pressure difference. The quantum vacuum is also related to one of the greatest mysteries of modern cosmology: dark energy. When physicists try to calculate the energy density of the quantum vacuum using the theories we know, they arrive at a number that is greater by a factor of approximately 10 to the power of 120 times than the dark energy density we observe, accelerating the expansion of the universe. This discrepancy is so absurdly large that it has been called the worst prediction error in the history of theoretical physics, and it reveals that there is something deeply flawed in our understanding of either quantum mechanics or gravity or both. Tyson also loves challenging people's intuitions about movement and rest. You probably feel like you're standing still right now as you read this, but in reality, you are moving at speeds that defy imagination in multiple frames of reference simultaneously. The Earth is rotating on its axis at approximately 1,600 kilometers per hour at the equator. You are being carried in that rotation right now. But the Earth is also orbiting the Sun at approximately 100,000 kilometers per hour, completing one revolution each year. The entire solar system is orbiting the center of the Milky Way at approximately 500,000 kilometers per hour, taking approximately 225 million years to complete one galactic orbit. And the Milky Way is moving relative to the cosmic microwave background radiation at approximately 400 miles per second, being pulled by the gravity of enormous galaxy clusters and superclusters. You are moving at all these speeds simultaneously, and yet you feel absolutely nothing because there is no absolute resting frame in the universe. All movement is relative to some other object or frame of reference. This is not just a philosophical curiosity. It is the essence of Galileo's relativity, which was later expanded and deepened by Einstein. There is no vantage point in the universe from which you can say, "Here is the true center. Here is where everything is really still." And where are you watching from now? Comment your city or country, because it's fascinating to think that people around the entire planet are discovering these same disturbing truths about the cosmos at the same time. All of us sharing this moment of collective mind expansion as Tyson guides us through the illusions we create about reality. The relativity of time is another concept that Tyson frequently addresses that completely destroys our intuition that time flows evenly for everyone, everywhere. Einstein demonstrated that time passes more slowly for objects moving relative to you, and also passes more slowly in stronger gravitational fields. These are not negligible effects only at speeds close to that of light, or in extreme black holes. They are measurable even in everyday situations. The GPS satellites that let your phone know where you are need to constantly correct their clocks, because time is passing slightly faster for them in orbit, where Earth's gravity is weaker compared to time on the surface. If this relativistic correction were not applied, your GPS would accumulate errors of several kilometers in just a few days. Astronauts who spend months on the International Space Station are literally traveling a few millionths of a second into the future relative to people on the surface, because they are moving at approximately 28,000 kilometers per hour in orbit. If you could travel in a spaceship at 99.9% the speed of light and come back, you would have aged only a few months, while decades would have passed on Earth. Your friends and family would be old while you would remain young, not because of some exotic biological effect, but simply because time literally passed slower for you. The composition of the universe is perhaps the most disturbing revelation that Tyson shares repeatedly. Everything we can see, from atoms to galaxies, everything made of protons, neutrons, and electrons, everything on the periodic table, every planet, star, nebula, black hole, absolutely everything, made of the matter we know and study, represents only approximately 5% of the total energy and mass content of the universe. The other 95% is divided between dark matter, approximately 27%, and dark energy, approximately 68%. Dark matter is called dark not because it is black, but because it does not interact with light in any way. It does not emit light, it does not reflect light, it does not absorb light. It is completely invisible to any electromagnetic telescope we can build. We know it exists only through its gravitational effects. Galaxies spin faster than they should if they contained only the visible matter we can see. And galaxy clusters warp the light from background galaxies in ways that require much more mass than we can directly observe. Dark energy is even more mysterious. It is a force or property of space that is causing the expansion of the universe to speed up, working against the gravity that should be slowing down the expansion. Discovered in 1998 through observations of distant supernovae, dark energy suggests that the ultimate fate of the universe may be an eternal accelerating expansion, where eventually all galaxies beyond our local group will be driven so far away by the expansion of space that their light will never reach us again, and the observable universe will progressively shrink until future civilizations, if they exist, see only darkness in all directions. Tyson also frequently shatters the illusion that chemical elements are eternal and immutable. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood were all forged in the cores of stars that lived and died billions of years before the sun existed. Hydrogen and helium were created in the first few minutes after the Big Bang, when the entire universe was hot and dense enough for nuclear fusion. but all the heavier elements, from carbon to uranium, were created by nuclear fusion inside stars or in supernova explosions. We are literally made of stardust, not as a poetic metaphor, but as a verifiable astrophysical fact. Massive stars live short, violent lives, fusing progressively heavier elements in their cores until they reach iron. And then, when their nuclear fuel runs out, they catastrophically collapse and explode as supernovae, scattering these heavy elements into space, where they eventually condense into new stars, planets, and, occasionally, life. The Sun and our entire solar system formed from a cloud of gas and dust that was enriched by the remains of countless previous generations of stars. When Tyson says, "We are the universe knowing itself," he is literally correct. We are arrangements of stellar atoms that have achieved sufficient complexity to contemplate their own cosmic origins. Another illusion that Tyson constantly dismantles is the idea that we see objective colors of the world. Reverse. The stunning images of colorful nebulae and vibrant galaxies that we see from space telescopes like Hubble or the James Webb are actually composites of multiple exposures at different wavelengths, often at wavelengths invisible to the human eye like infrared or X-rays, which are then mapped to visible colors in an arbitrary but scientifically informed way. If you could travel to a nebula and look at it directly with your eyes, it would probably look like a very faint gray blur because nebulae are incredibly diffuse. The average density is a better vacuum than anything we can create in terrestrial laboratories, and our eyes are not sensitive enough to pick up the faint light scattered by such large volumes of rarefied gas. Telescope cameras take exposures lasting hours or even days, accumulating photons that our eyes could never collect in real time. This doesn't mean the images are fake. They reveal real physical structures and processes, but they are visual translations of electromagnetic data, not direct photographs like you would take with a regular camera. Tyson also loves to challenge our understanding of dimensions. We live in a three-dimensional world. We can move up or down, left or right, forward or back. And these three spatial dimensions seem to exhaust all possible directions of movement. But string theory, one of the most ambitious attempts to unify quantum mechanics and general relativity, suggests that there may be 6 or 7 additional spatial dimensions beyond the 3 we experience, all rolled up on incredibly small scales, smaller than the atomic nucleus. On these tiny scales, the fundamental particles that we think of as dimensionless points would actually be vibrating strings, and different patterns of vibration would correspond to different particles like electrons, quarks, photons. Although string theory remains unproven and highly speculative, it represents a profound attempt to imagine that reality may have layers of dimensional complexity that are completely beyond our ability to directly visualize, accessible only through mathematics and indirect experiments. The issue of extraterrestrial life is another area where Tyson reveals how much our intuition deceives us. Many people assume that if intelligent life existed elsewhere in the galaxy, we would already have detected signs of it, or it would have visited us. This is the famous Fermi paradox. But Tyson points out the scales involved. The Milky Way contains between 200 and 400 billion stars spread across a disk approximately 100,000 light-years across. Even if technological civilizations were relatively common, the distances between them would be so vast that communication would be incredibly difficult, and interstellar travel would take thousands or millions of years with any conceivable propulsion technology. Furthermore, civilizations can exist at different times. One civilization may have flourished and disappeared millions of years ago, while another has not yet evolved. There is also the possibility that technological civilizations tend to self-destruct on relatively short timescales after developing technology capable of altering their planetary environment or creating weapons of mass destruction. Tyson also frequently mentions that we look for life using very terrestrial criteria, assuming that life needs liquid water, an oxygen-rich atmosphere, moderate temperatures, but radically different life forms could exist in environments that we would consider completely inhospitable, using chemistry completely different from the carbon-based biology we know. The very concept of an observable universe is an illusion of perspective that Tyson loves to explore. When we talk about the observable universe, we are talking about a sphere with a radius of approximately 46.5 billion light-years centered on us, not because we are special, but simply because it is the limit of how far light has had time to travel to us since the Big Bang. But the total universe may be infinitely larger than this observable region. It may literally be infinite in all directions, containing infinite galaxies, infinite stars, infinite planets. Beyond the observable horizon, there may be regions of space that are expanding away from us faster than the speed of light, not because they are moving through space at that speed, which would violate relativity, but because the space itself between us and these regions is expanding so quickly that light from them will never reach us. These regions are permanently causally disconnected from us. Events happening there can never affect us, and we can never affect them, even in principle. There is also the possibility raised by cosmic inflation that there may be other universes, completely separate bubbles of space-time with their own physical laws, different constants, different evolutionary history, a multiverse where our observable universe is just a small bubble in an infinite ocean of other universes. Tyson also frequently addresses how our understanding of black holes reveals fundamental limits of knowledge. A black hole is formed when a massive star collapses under its own gravity into a point of infinite density called a singularity, surrounded by an event horizon, a boundary beyond which not even light can escape. A black hole's gravity is so intense that it distorts the fabric of space-time in extreme ways predicted by general relativity. But at the singularity, all our physical theories break down. General relativity predicts infinite density and infinite curvature. But these infinities signal that the theory has reached its limits of applicability. We need a quantum theory of gravity to truly understand what happens at the heart of a black hole. And despite decades of intense theoretical work, we still don't have such a theory. Stephen Hawking showed that black holes are not completely black. They emit quantum radiation and eventually evaporate. But this creates the black hole information paradox. Quantum information falling into a black hole appears to be destroyed when the black hole evaporates, violating fundamental principles of quantum mechanics. This paradox remains unresolved and points to deep gaps in our understanding of how gravity and quantum mechanics relate. The nature of time itself is something that Tyson reveals to be much stranger than our experience suggests. In fundamental physics, almost all equations are symmetric in time. They work equally well whether you rotate time forward or backward. But our experience is deeply asymmetrical. Eggs break, but do not reconstitute themselves spontaneously. We age, but do not rejuvenate. The past is fixed, while the future remains open. This asymmetry comes from the second law of thermodynamics, which says that entropy, a measure of disorder, tends to increase in closed systems. But this just pushes the question a level deeper. Why did the early universe have such low entropy? The Big Bang represents the lowest entropy state the universe has ever had, highly ordered and uniform, and since then, entropy has consistently increased. If the universe had started in a state of high entropy, there would be no arrow of time, there would be no preferred direction, events could happen in any temporal order. The initial low entropy of the universe is one of the deepest cosmological mysteries, and is closely related to the very concept of time having a direction. Tyson also constantly highlights that quantum mechanics reveals that reality is fundamentally probabilistic at its most fundamental scales. Before you observe a quantum particle, it has no defined position or defined momentum. It exists in a superposition of all possible states simultaneously. Only when you make a measurement does the wave function collapse, and the particle takes on definite values. This isn't just ignorance on our part about where the particle actually is, it's a fundamental indeterminacy in the very nature of reality. Einstein famously disliked this interpretation, saying, "God doesn't play dice with the universe." He believed there must be hidden variables that determine outcomes, if only we can access them. But experiments testing Bell's inequalities have shown that local hidden variables cannot explain the observed quantum correlations. Nature actually appears to be fundamentally indeterministic on microscopic scales. Even more strangely, quantum entanglement allows particles to remain correlated instantaneously across arbitrary distances. If you measure the spin of an entangled electron here, you instantly know the spin of its entangled partner on the other side of the galaxy, even though the information about your measurement cannot travel faster than light. Einstein called it spooky action at a distance and was deeply disturbed by it, but experiments have repeatedly confirmed that quantum entanglement is real. The question of how something came from nothing is also an area where Tyson reveals how much modern physics defies philosophical intuition. The first law of thermodynamics says that energy can neither be created nor destroyed. So how did the universe come to be? One possible answer comes from quantum gravity. The total energy of the universe could be exactly zero, with the positive energy of matter and radiation exactly cancelled out by the negative gravitational energy. If the universe had like a quantum vacuum fluctuation, an entire universe could arise spontaneously without violating conservation of energy. This sounds absurd. Universes don't just appear out of nowhere, but on quantum scales things actually appear out of nowhere all the time. And if the universe was smaller than the Planck length in its earliest moments, it was in the quantum domain where such fluctuations are possible. This doesn't completely resolve the issue because you still need physical laws and a quantum vacuum for the fluctuations to happen, so you're not really starting from absolute nothing, but it does suggest that the concept of creation may not make sense in the way we philosophically imagine it. As we explore these disturbing revelations about the nature of reality, Tyson also emphasizes the importance of scientific humility. Each generation of scientists thought they were close to understanding everything, and each generation discovered that the universe had additional layers of complexity and strangeness that no one had predicted. The ancient Greeks thought they understood the cosmos with its crystalline, celestial spheres. Newton thought classical mechanics and universal gravitation explained everything. In the late 19th century, some physicists declared that physics was essentially complete. Only a few details needed to be resolved. And then relativity and quantum mechanics exploded these certainties completely. Today we know that our current understanding is incomplete. We don't know what dark matter or dark energy make up 95% of the universe. We don't have a quantum theory of gravity. We don't fully understand what happened in the first trillionth of a second after the Big Bang. We don't know if there are extra dimensions or other universes. We don't know if consciousness is a purely physical phenomenon or requires new principles. We don't know if life and intelligence are rare or common in the cosmos. Tyson's revelations are not just about what we know, but about the vast ocean of what we don't yet know. And probably what we don't even know we don't know. The anthropic principle is another area where Tyson challenges our intuitions about meaning and purpose. We observe that the fundamental constants of nature, things like the force of gravity, the charge of the electron, the cosmological constant, appear to be finely tuned to allow for the existence of complex atoms, long-lived stars, rich chemistry, and, eventually, life. If the strong nuclear force were slightly different, atomic nuclei could not form. If gravity were slightly stronger, stars would burn their fuel too quickly for planets to evolve life. If dark energy were much greater, the universe would have expanded too quickly for galaxies to form. Some people see this fine-tuning as evidence of intentional design, but the anthropic principle offers an alternative explanation. In a multiverse with infinite universes having different values for these constants, only universes where the constants allow for complex observers will have observers to marvel at the fine-tuning. It's not that the universe was designed for us, it's that we could only exist in the kind of universe that allows us to exist, so we naturally observe that we live in such a universe. This doesn't completely resolve the issue, but it shows how questions about cosmic purpose can have answers that challenge both theology and common philosophical intuitions. Tyson also frequently discusses how the finite speed of light creates a curious temporal asymmetry. We can see the distant past by looking far into space, but we can never see the future. The deeper our telescopes penetrate the cosmos, the younger the universe we are observing. The James Webb Space Telescope can detect galaxies that formed just a few 100 million years after the Big Bang. We are literally observing the first generations of stars lighting up the dark early universe. But we can never observe the future. We can't see how these early galaxies will evolve. We can only make theoretical models and hope that they correspond with observations of galaxies at different evolutionary stages. There is a fundamental boundary between the observable and the unobservable, and it is not just a technological limitation but an intrinsic characteristic of living in a universe where information travels at finite speed and where space itself is expanding. The question of free will versus determinism also appears in Tyson's revelations about physics. If the universe at the fundamental level is governed by deterministic physical laws, then in principle, the future state of the universe is completely determined by the present state and the laws that govern evolution. Every thought you have, every decision you make, it would be the inevitable result of particles and fields obeying blind physical laws. This seems to conflict with our subjective experience of making free decisions. Quantum mechanics introduces genuine indeterminism, but it is random indeterminism, not conscious choice, so it is unclear whether this actually saves free will in any meaningful sense. Neuroscientists have also shown that decisions can be predicted from brain activity seconds before you consciously feel like you've made the decision. This raises profound questions about the nature of consciousness, agency, and moral responsibility that Tyson recognizes are at the frontiers of what science can currently address. If these revelations have blown your mind as much as they blow mine every time I contemplate these cosmic truths, leave a like, subscribe to the channel, and turn on notifications because we have many more mysteries of the universe to unravel together. And each scientific discovery we share is an opportunity to expand our collective understanding of this extraordinary reality we inhabit. The universe that Tyson reveals is not the comfortable, intuitive universe that our minds have evolved to navigate. It is a cosmos vastly larger, stranger, more beautiful, and scarier than any ancient mythology could have imagined. We are intelligent monkeys on an average planet, orbiting an ordinary star, in a spiral arm of a typical galaxy in a universe containing trillions of galaxies. And yet, we have developed mathematics, physics, telescopes, and space probes that allow us to unlock the deepest secrets of reality. We are composed of atoms forged in dead stars billions of years ago. We are made of the same substance as planets and nebulae and black holes. There is no fundamental separation between us and the cosmos. We are the universe becoming aware of itself, asking questions about its own origins and destiny. Tyson's revelations about the counterintuitive nature of the cosmos serve as a powerful reminder that reality is under no obligation to make intuitive sense to creatures that evolved to survive on African savannas. Our intuition was shaped by natural selection to deal with medium-sized objects moving at medium speeds in weak gravitational fields. It serves us well in our everyday environment, but completely misleads us when we try to understand the very small, the very large, the very fast, or the very massive. Science is the tool we develop to transcend these limitations, using mathematics, controlled experiments, precise instruments, and rigorous logical reasoning to discover truths about the universe that no amount of philosophical introspection or mystical revelation could achieve. Every scientific revelation that seems counterintuitive is not a failure of science, but a testimony to its power. It is showing us a deeper reality beyond the superficial appearances that our senses present. The work of popularizers like Neil deGrasse Tyson is crucial because science does not just belong to scientists, it belongs to all of humanity. Discoveries about the nature of space, time, matter, and energy impact how we understand our place in the cosmos, inform decisions about technology and politics, and satisfy deeply human curiosity about where we came from and where we are going. When Tyson dismantles the comfortable illusions we have about the universe, he is not being destructive, he is being liberating. He is inviting us to embrace a truer, richer understanding of reality, even when that understanding challenges our most basic intuitions. The universe that modern science reveals is more wonderful than ancient mythmakers could have dreamed of. It is a universe where space and time are dynamic and intertwined, where particles can be in multiple places simultaneously, where dark energy is tearing through the cosmos at an accelerated pace, where black holes distort the very geometry of reality, where billions of years of cosmic evolution have created the conditions for matter to organize itself into patterns capable of contemplating its own origins. As we conclude this journey through Tyson's revelations about the comfortable lies we tell ourselves about space, it becomes clear that the true value of science lies not in confirming what we already think we know, but in constantly challenging and expanding the limits of human knowledge. Each generation inherits a conceptual universe built by the discoveries of previous generations and has the opportunity and responsibility to question, test, and expand it. The revelations Tyson shares are not endpoints, but starting points. Each scientific answer opens up new, deeper questions. Each mystery solved reveals additional mysteries waiting to be explored. The cosmos. It is not a static puzzle to be solved, but a dynamic process of never-ending discovery. And we have the extraordinary privilege of living in an era where our technology and understanding allow us to ask questions and seek answers about the most fundamental questions of existence. When you look up at the night sky tonight, remember that you are not seeing a static landscape, but a window into the past, into physical processes of incomprehensible scale and power, into a universe that is simultaneously our home and completely alien to our intuitive experience. And that this tension between familiarity and strangeness is precisely what makes the scientific exploration of the cosmos one of the most profound and significant endeavors humanity has ever undertaken.